Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the remote Galapagos Islands, 600 miles off Ecuador's coast, Charles Darwin encountered something extraordinary in 1835. The finches, he observed, weren't just surviving, they were adapting with remarkable precision. Today, scientists recognize these birds as living laboratories of evolution. But what if their story had taken a different turn? What if, instead of merely developing specialized beaks, they had evolved the capacity for complex language? The question isn't as fantastical as it might seem. Communication represents one of evolution's most powerful tools, and birds already demonstrate remarkable cognitive abilities. African grey parrots can learn over 100 words and use them contextually. Corvids, crows, ravens, and jays solve multi-step puzzles and demonstrate self-awareness. New Caledonian crows craft sophisticated tools, passing techniques through generations via cultural transmission. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The neural architecture for language already exists in modified forms throughout the animal kingdom. Songbirds possess specialized brain regions analogous to human language centers. The high vocal center, or HVC, processes complex acoustic patterns, while Area X controls vocal learning, mechanisms that could theoretically support linguistic development far beyond current capabilities. Darwin's finches exhibit behavioral flexibility that surpasses many bird species. They demonstrate social learning, transmit cultural information, and adapt their foraging strategies based on environmental feedback. Ground finches alter their beak usage patterns within a single generation when food sources change. Tree finches modify nest construction techniques based on local materials and predation pressures. The evolutionary pressure for enhanced communication would likely emerge from environmental challenges unique to island ecosystems. Limited resources create intense competition, favoring individuals who can coordinate complex group behaviors. Finches already engage in sophisticated social hierarchies, with dominant individuals controlling prime feeding territories, while subordinates develop alternative strategies. Language evolution requires three critical components: cognitive capacity, anatomical capability, and selective pressure. Finches possess enlarged forebrains relative to their body size, indicating advanced processing power. Their syrinx, the avian equivalent of a larynx, already produces varied acoustic signals for territory defense, mate attraction, and alarm calls. The selective advantage of proto-language would manifest through improved resource sharing, predator detection, and cooperative breeding. Finches that could communicate precise information about food locations, predator types, or environmental hazards would outcompete less articulate relatives. Over thousands of generations, this advantage would compound, driving increasingly sophisticated communication systems. Neuroplasticity studies reveal that songbird brains restructure throughout their lives, adding new neurons to vocal control regions during learning periods. This neural flexibility provides the biological foundation for expanding communication repertoires. Young finches already undergo critical learning periods where they acquire species-specific songs through social interaction, a process remarkably similar to human language acquisition. The Galapagos environment offers unique conditions for linguistic evolution. Geographic isolation prevents genetic dilution from mainland populations, while island-to-island separation could drive dialectical diversification. Each island's distinct ecological challenges might favor different communication strategies, creating the foundation for multiple finch languages. Recent studies using high-resolution acoustic monitoring reveal that finch vocalizations contain far more complexity than previously recognized. Spectrograms show layered frequency patterns, temporal variations, and contextual modifications that suggest rudimentary syntax. These discoveries hint that the evolutionary leap to true language might be smaller than scientists traditionally assumed. The implications extend far beyond ornithology. Understanding how language could evolve in non-human species illuminates the fundamental principles governing all communication systems, potentially revealing universal patterns that govern intelligence throughout the cosmos. The transformation from simple songbird to linguistic communicator would require dramatic neural reorganization, yet evolution has precedents for such cognitive leaps. The human brain tripled in size over 3 million years, developing specialized regions for language processing, abstract reasoning, and cultural transmission. A similar revolution in finch neuroanatomy could theoretically occur under the right selective pressures. Modern neuroscience reveals that songbird brains contain remarkable parallels to human language centers. The robust nucleus of the archipallium, or RA, corresponds functionally to Broca's area, controlling vocal production and motor coordination. The caudomedial nidopallium, or NCM, processes auditory information similarly to Wernicke's area, interpreting acoustic patterns and extracting meaning from complex vocalizations. The hypothetical evolution of finch language would begin with expanded neural connectivity between existing brain regions. Current research shows that London taxi drivers develop enlarged hippocampi from navigating complex street networks. Similarly, linguistically evolving finches would experience growth in regions connecting auditory processing, motor control, and memory formation. Synaptic plasticity would accelerate under communicative demands. Finches already demonstrate seasonal neurogenesis, growing new neurons for song learning during breeding periods. Enhanced linguistic abilities would require year-round neural flexibility, potentially leading to brains that continuously reorganize. Throughout their lifespans, the development of symbolic thinking represents the most significant cognitive leap. Current finches associate specific calls with immediate situations, predator alarms, territorial displays, or mating advertisements. True language requires abstracting beyond immediate contexts, using arbitrary sounds to represent concepts, objects, or ideas not physically present. Archaeological evidence suggests human symbolic thinking emerged approximately 70,000 years ago, coinciding with dramatic behavioral changes including art production, complex tool manufacture, and long-distance trade networks. A finch cognitive revolution might follow similar patterns, beginning with simple symbol manipulation, before expanding into complex conceptual frameworks. Memory systems would undergo substantial enhancement to support linguistic cognition. Current finches remember dozens of individual songs, territorial boundaries, and seasonal food sources. Language-capable finches would require exponentially expanded working memory to manipulate abstract concepts, construct novel utterances, and maintain conversational context across extended interactions. The evolution of theory of mind, understanding that other individuals possess different knowledge, beliefs, and intentions, would prove crucial for linguistic development. Current research indicates some corvids demonstrate primitive theory of mind, adjusting their caching behavior when observed by potential thieves. Finches would need similar cognitive abilities to engage in meaningful communication about absent objects or abstract concepts. Temporal reasoning would expand dramatically as finches developed linguistic capabilities. Current bird cognition focuses primarily on immediate needs and seasonal cycles. Language using finches would require enhanced abilities to discuss past events, plan future activities, and consider hypothetical scenarios, cognitive skills that would fundamentally alter their ecological relationships. The social brain hypothesis suggests that intelligence evolved primarily to navigate complex social environments. Linguistically enhanced finches would develop increasingly sophisticated social cognition, tracking individual relationships, reputation systems, and cultural hierarchies across multi-generational communities. Neural lateralization, the specialization of brain hemispheres for different functions, would likely emerge in language using finches. Humans show strong left hemisphere dominance for language processing, while songbirds display similar patterns for vocal learning and production. Enhanced lateralization would improve processing efficiency and cognitive capacity. The development of recursive thinking, the ability to embed concepts within other concepts infinitely, would represent the final cognitive breakthrough. This uniquely human trait allows for complex grammatical structures and abstract reasoning. Finches achieving recursive cognition would gain unprecedented problem-solving abilities and cultural transmission capabilities. Epigenetic factors would play crucial roles in cognitive evolution. Environmental stresses, social interactions, and learning experiences modify gene expression patterns that affect brain development. Linguistically evolving finch populations would likely show increased epigenetic diversity, providing raw material for continued cognitive enhancement. The energetic costs of enhanced cognition would create new evolutionary pressures. Brains consume approximately 20% of human metabolic energy, despite representing only 2% of body weight. Language-capable finches would require significant dietary improvements or metabolic efficiency gains to support expanded neural processing. The evolution of complex vocalization requires more than cognitive enhancement. It demands fundamental anatomical restructuring throughout the respiratory and vocal systems. Current finch anatomy already surpasses mammalian capabilities in some respects, providing an excellent foundation for further vocal evolution. The avian syrinx represents a masterpiece of evolutionary engineering. Located at the junction where the trachea splits into bronchi, this dual-chambered structure allows birds to produce two independent sound streams simultaneously. Unlike the mammalian larynx, which vibrates vocal cords through exhaled air, the syrinx uses specialized muscles and membranes to create incredibly diverse acoustic outputs. Enhanced language capabilities would drive syrinx modifications toward greater precision and control. Current finches possess approximately 4 to 6 pairs of intrinsic syringeal muscles controlling sound production. Language-capable finches might evolve 12 to 16 muscle pairs, enabling articulation complexity approaching human speech capabilities while maintaining their unique dual voice advantages. The respiratory system would undergo significant modifications to support extended vocalizations. Current songbirds use approximately 9 air sacs connected to their lungs, creating continuous airflow during both inhalation and exhalation. This system already surpasses mammalian respiratory efficiency, but language demands would favor enlarged air sacs and enhanced muscular control for sustained vocal output. Beak morphology would face evolutionary pressure from dual demands: traditional foraging efficiency and vocal articulation. Current Darwin's finches show remarkable beak diversity, adapted to specific food sources. Large ground finches crack tough seeds with powerful, thick beaks, while warbler finches probe bark crevices with thin, pointed bills. Language-using finches might develop more flexible beak structures, possibly with enhanced muscular control, allowing shape modifications during vocalization. Alternatively, different finch species might specialize in distinct acoustic ranges, creating natural dialect boundaries based on anatomical capabilities rather than geographic separation. The tongue and oral cavity would require substantial enhancement for precise sound modification. Current finch tongues are relatively simple structures, adapted primarily for food manipulation. Language-capable finches would likely evolve more complex tongue anatomy with increased muscular control, similar to the extraordinary modifications seen in woodpecker tongues, which can extend far beyond beak length. Neural control pathways would expand dramatically to coordinate these anatomical enhancements. The hypoglossal nerve controlling tongue movement would require increased myelination and branching to enable rapid, precise articulation. Similarly, the syringeal branches of the vagus nerve would need enhanced capacity to coordinate complex muscle interactions. Hearing systems would co-evolve with vocal capabilities to process increasingly sophisticated acoustic information. Current finches already possess excellent auditory discrimination, distinguishing individual voices and subtle frequency variations. Enhanced language abilities would drive further improvements in temporal resolution, frequency discrimination, and noise filtering capabilities. The development of specialized resonance chambers could amplify vocal complexity without increasing metabolic costs. Some current songbirds use their beaks, throat pouches, or even inflated esophagi as resonance chambers. Language-capable finches might evolve dedicated vocal resonance structures, possibly including expandable throat sacs or modified skull cavities. Breathing pattern modifications would become essential for sustained speech production. Current songbirds coordinate vocalization with respiratory cycles, often producing complex songs during single exhalations. Language using finches would need enhanced voluntary breathing control, allowing speech production independent of metabolic respiratory needs. The evolution of facial expression capabilities might accompany vocal enhancement. Many social mammals use facial expressions to supplement vocal communication. While birds lack facial muscles comparable to mammals, enhanced feather control around the head and neck regions could provide visual communication supplements to vocal language. Developmental plasticity would increase to accommodate diverse vocal learning requirements. Current songbirds show critical periods for vocal development, typically during their first year of life. Language-capable finches might evolve extended or multiple critical periods, allowing continued vocal learning throughout their lifespans. Sexual dimorphism in vocal anatomy might emerge or intensify as language capabilities develop. Many current songbird species show sex-specific vocal differences, typically with males producing more complex songs for territorial and mating displays. Language evolution might reduce these differences as communication becomes essential for both sexes, or alternatively, it might enhance dimorphism. As different acoustic roles emerge within social groups, the integration of all these anatomical modifications would require precise developmental coordination. Genetic regulatory networks controlling vocal system development would become increasingly complex, potentially making language-capable finches more vulnerable to developmental disruptions, but also providing greater evolutionary flexibility for continued vocal enhancement. The Galapagos archipelago creates unique evolutionary pressures that could theoretically drive language development in finch populations. These volcanic islands, formed over millions of years, present constantly changing environmental challenges that reward behavioral flexibility and social cooperation, exactly the conditions that favor enhanced communication systems. Climate variability represents the primary selective pressure shaping Galapagos ecology. El Niño events occur every 3 to 7 years, dramatically altering rainfall patterns and food availability. During El Niño years, seed production increases dramatically, favoring large-beaked finches capable of exploiting abundant resources. La Niña years bring drought conditions, creating intense competition for scarce resources and favoring smaller, more efficient species. These cyclical environmental changes would strongly favor finches capable of communicating complex information about resource locations, quality, and availability. Current finches already demonstrate some information sharing through observational learning, but true linguistic capabilities would provide enormous advantages during resource-scarce periods. Predation pressure adds another layer of selective advantage for enhanced communication. The Galapagos hosts several introduced predator species, including cats, rats, and fire ants, alongside native predators like short-eared owls and Galapagos hawks. Effective predator warning systems require more than simple alarm calls. They benefit from detailed information about predator type, location, behavior, and threat level. Language-capable finches could develop sophisticated predator communication networks, sharing precise information about hunting patterns, safe refuges, and effective escape strategies. This information sharing would be particularly valuable for inexperienced juveniles learning to navigate dangerous environments. Cooperative breeding behaviors already exist in some finch populations, particularly during harsh environmental conditions. Related individuals sometimes assist with nest construction, territory defense, and chick feeding. Enhanced communication abilities would facilitate more complex cooperative arrangements, including coordinated foraging expeditions, shared territorial, defense, and collective childcare systems. The patchy distribution of resources across different islands would favor finches capable of communicating about distant food sources or environmental conditions. Current finches show limited inter-island movement, but language-capable birds might develop cultural transmission systems for sharing information about conditions on neighboring islands, potentially facilitating adaptive migration patterns. Interspecific Competition among the 14 finch species creates additional pressures favoring communication advantages. Different species often compete for overlapping resources, particularly during drought periods when specialized food sources become scarce. Enhanced intraspecific communication could provide competitive advantages through improved resource exploitation strategies and territorial coordination. The evolution of cultural transmission would provide cumulative advantages across generations. Current finches show limited cultural learning, primarily in song acquisition and some foraging techniques. Language-capable finches could develop rich cultural traditions, accumulating environmental knowledge, survival strategies, and technological innovations across multiple generations. Mate selection would become increasingly complex in language-using finch populations. Current finch mating systems rely heavily on song complexity, plumage characteristics, and territory quality. Linguistic abilities might become primary mate selection criteria, favoring individuals capable of complex communication and cultural knowledge transmission. Tool use, currently limited to a few finch species using cactus spines for insect extraction, could expand dramatically with enhanced communication capabilities. Language would facilitate tool-making instruction, technique refinement, and innovation sharing across populations, potentially leading to sophisticated technological cultures. Disease pressure might favor communication-enhanced populations through improved health information sharing. The Galapagos ecosystem faces ongoing threats from introduced pathogens and parasites. Finches capable of communicating about disease symptoms, treatment behaviors, or contaminated areas might show improved survival rates during epidemic events. Seasonal migration patterns could become more sophisticated with enhanced communication abilities. While most Galapagos finches show limited seasonal movement, language-capable populations might develop complex migration strategies based on shared environmental knowledge, weather prediction, and resource forecasting. The establishment of trade relationships between different finch populations might emerge as language capabilities develop. Different islands and habitats provide different resources. Some offer abundant seeds, others provide nesting materials, and some have superior water sources. Communication-enabled finches might develop resource exchange systems, sharing materials, and information across territorial boundaries. Climate change presents emerging selective pressures that could favor linguistically enhanced finch populations. Rising sea levels, changing precipitation patterns, and shifting vegetation zones will require rapid behavioral adaptations. Populations capable of sharing environmental information and coordinating adaptive responses would likely show improved survival rates compared to non-communicating relatives. The evolution of language would fundamentally transform finch social organization, potentially leading to complex hierarchical societies rivaling those of social mammals. Current finch social structures are relatively simple, based primarily on breeding pairs, loose foraging flocks, and temporary territorial associations. Enhanced communication capabilities would enable far more sophisticated social arrangements. Cultural transmission would emerge as the primary driver of finch civilization development. Unlike genetic inheritance, which passes information vertically, from parent to offspring, cultural transmission allows horizontal information sharing across peer groups and even between species. Language-capable finches could accumulate knowledge exponentially, building upon previous generations' discoveries while innovating new solutions to environmental challenges. The development of social hierarchies would likely follow patterns observed in other highly intelligent species. Current finch dominance relationships are straightforward, typically based on size, age, and territorial ownership. Language-enabled societies might develop complex status systems based on knowledge possession, communication skills, or cultural contributions rather than purely physical attributes. Specialized social roles would emerge as finch societies increased in complexity. Some individuals might become dedicated environmental monitors, tracking weather patterns and resource availability across large territories. Others might specialize in intergroup diplomacy, facilitating communication and cooperation between different finch communities. Cultural knowledge keepers would preserve and transmit important survival information across generations. The evolution of teaching behaviors would accelerate cultural development dramatically. Current finches show limited instructional behavior, primarily through observational learning and occasional food sharing with offspring. Language-capable finches could develop formal educational systems, with experienced adults systematically instructing juveniles in essential survival skills, environmental knowledge, and cultural practices. Conflict resolution mechanisms would become increasingly sophisticated as social complexity increased. Simple dominance displays and territorial aggression would prove inadequate for managing complex multi-group relationships. Language-enabled finches might develop elaborate negotiation protocols, arbitration systems, and even primitive legal frameworks for managing disputes and resource allocation. The emergence of distinct cultural groups would likely follow geographic and ecological boundaries. Different islands or habitat types would favor different survival strategies, leading to divergent cultural traditions. Tree-dwelling finch populations might develop sophisticated arboreal navigation systems and canopy-specific survival techniques, while ground-dwelling groups would focus on terrestrial resource exploitation and predator avoidance. Trade relationships between different finch communities would become increasingly complex as specialization developed. Island populations with superior nesting materials might exchange resources with communities possessing better food sources or water access. These trading relationships would require sophisticated communication protocols for negotiating exchanges, maintaining agreements, and resolving disputes. Religious or spiritual belief systems might emerge in highly developed finch societies. Many intelligent species demonstrate behaviors suggesting awareness of death, environmental cycles, and natural phenomena beyond immediate survival needs. Language-capable finches might develop explanatory frameworks for natural events, seasonal changes, and life cycle transitions, potentially leading to ritualistic behaviors and cultural practices. Artistic expression would likely accompany advanced cultural development. Current songbirds already demonstrate aesthetic preferences in song composition, mate selection, and nest decoration. Enhanced communication abilities might enable sophisticated artistic traditions, including complex musical compositions, decorative crafts, and possibly even primitive visual arts using available materials. The development of historical consciousness would distinguish advanced finch cultures from current animal societies. Language enables abstract temporal reasoning, allowing individuals to conceptualize past events, current conditions, and future possibilities simultaneously. Finch cultures might develop historical narratives, preserving important events and cultural memories across multiple generations. Innovation and technological development would accelerate through cultural transmission. Current tool use among finches is limited and shows little improvement across generations. Language-enabled populations could systematically refine techniques, share innovations, and develop increasingly sophisticated technologies for food acquisition, shelter construction, and environmental manipulation. Social institutions would emerge to manage increasingly complex community interactions. Leadership structures might evolve beyond simple dominance hierarchies, potentially including elected representatives, specialist advisors, or council-based decision-making systems. These institutions would require sophisticated communication, protocols, and cultural agreements about authority and responsibility. Population regulation mechanisms would become necessary as finch societies grew more complex and resource-intensive. Current finch populations are regulated primarily through environmental limitations and territorial competition. Advanced societies might develop cultural practices governing reproduction, resource consumption, and territorial expansion to maintain sustainable population levels. The potential for interspecies communication and cooperation would increase dramatically with enhanced linguistic capabilities. Different finch species might overcome current competitive relationships, developing cooperative frameworks based on complementary specializations and mutual benefit rather than resource competition alone. The intersection of enhanced cognition, sophisticated communication, and cultural transmission would enable finch societies to develop technologies far beyond current avian capabilities. While tool use among birds remains limited to simple implementations, new Caledonian crows crafting hooked sticks, Egyptian vultures throwing stones, language-capable finches could theoretically achieve technological sophistication approaching early human civilizations. Construction techniques would evolve dramatically from current nest-building behaviors. Contemporary finches construct relatively simple nests using available materials with minimal modification. Enhanced cognitive abilities and cultural knowledge transmission could lead to sophisticated architectural achievements, including multi-chamber structures, weatherproofing innovations, and communal construction projects requiring coordinated group effort. Agricultural practices might emerge as finch societies developed deeper understanding of plant ecology and seasonal cycles. Current finches show limited environmental modification beyond basic territory maintenance. Language-enabled populations could potentially develop seed cultivation techniques, selective plant management, and even primitive irrigation systems. Using natural water sources and rainfall patterns, the development of specialized tools would transform finch ecological relationships. Beyond simple probe tools currently used by some species, advanced finch societies might create complex implements for specific tasks, harvesting tools for different seed types, construction implements for nest building, and even crude weapons for territorial defense or predator deterrence. Cooperative hunting and foraging strategies would become increasingly sophisticated through enhanced communication capabilities. Current finches occasionally engage in loose flocking behaviors that provide some foraging advantages, but true cooperative strategies remain limited. Language-capable finches could coordinate complex group hunts, systematic territory surveys, and efficient resource exploitation patterns. Engineering projects might emerge to address environmental challenges unique to island ecosystems. Water, collection and storage systems could help communities survive drought periods. Shelter construction might evolve to protect against extreme weather events. Even primitive bridge building using natural materials could facilitate movement between terrain features or island sections. The development of measurement and quantification systems would enable increasingly precise resource management. Current animals demonstrate basic quantity discrimination, distinguishing between larger and smaller amounts, but lack symbolic numerical systems. Language-capable finches might develop counting systems, measurement standards, and resource accounting methods enabling sophisticated community planning. Medical and health practices could evolve through systematic observation and knowledge sharing. Many current animals engage in self-medication behaviors, consuming specific plants or minerals to address health issues. Language-enabled finch societies could systematically document these practices, refine treatment techniques, and develop community health management systems. Transportation technologies might develop to address inter-island movement challenges. While finches are naturally capable flyers, advanced societies might create tools to assist with long-distance travel, weather navigation, or cargo transport. Simple rafts or flotation devices could enable resource transport across water barriers. Food, processing, and preservation techniques would provide significant survival advantages during resource-scarce periods. Current finches consume foods with minimal processing beyond basic hull removal. Advanced societies might develop techniques for food storage, processing methods to improve nutrition extraction, and preservation systems extending food availability. During harsh seasons, communication technologies could extend beyond direct vocal interaction. Visual signaling systems using environmental modifications, marker placement, or collaborative displays might enable long-distance communication across territorial boundaries. These systems could warn of dangers, indicate resource availability, or coordinate complex multi-group activities. Quality control and standardization would become important as technological complexity increased. Simple tools require minimal precision, but sophisticated implements demand consistent materials, accurate measurements, and reliable construction techniques. Advanced finch societies would need to develop quality assessment methods and standardization protocols. The emergence of specialized manufacturing roles would accompany technological development. Different individuals might specialize in specific tool creation, construction techniques, or resource processing methods. This specialization would require sophisticated training systems and knowledge transfer protocols, enabled by enhanced communication capabilities. Innovation diffusion mechanisms would accelerate technological advancement across populations. New discoveries or technique improvements could spread rapidly through language-enabled communities, allowing beneficial innovations to reach all population members quickly. This rapid diffusion would accelerate the pace of technological advancement significantly. Maintenance and repair protocols would become essential as finch technologies increased in complexity. Simple nests require minimal upkeep, but sophisticated structures and tools need regular maintenance to remain functional. Advanced societies would develop systematic maintenance schedules, repair techniques, and replacement protocols for community technologies. The potential for inter-community technology sharing would create opportunities for rapid advancement through cultural exchange. Different finch populations facing different environmental challenges might develop specialized solutions that could benefit other communities. Language-enabled trade relationships could facilitate technology transfer alongside resource exchange. Resource, recycling and waste management would become increasingly important as finch societies developed more complex material cultures. Current animal societies produce minimal waste, but technological development creates disposal challenges. Advanced finch communities might develop recycling systems and waste management protocols to maintain environmental sustainability. The theoretical evolution of language-capable finches would provide unprecedented insights into the fundamental principles governing intelligence, communication, and civilization development throughout the universe. Such a development would represent only the second known emergence of complex language on Earth, offering crucial comparative data for understanding whether human cognitive evolution follows universal patterns or represents a unique historical accident. Astrobiology implications would be profound, as language-capable finches would demonstrate that complex communication can evolve through multiple independent pathways. Current astrobiology research focuses heavily on identifying potentially habitable planets and detecting chemical signatures of life, but the discovery of alternative intelligence evolution would fundamentally alter search strategies for communicating extraterrestrial civilizations. The study of parallel cognitive evolution would illuminate which aspects of intelligence represent convergent solutions to universal problems versus unique adaptations to specific environments. Human language evolution occurred within specific ecological and social contexts that might not be reproducible elsewhere in the universe. Finch language evolution would reveal whether similar cognitive capabilities can emerge under different environmental pressures and anatomical constraints. Comparative linguistics would expand beyond human language families to include entirely different evolutionary origins. Current linguistic research examines how human languages diversify and change over time, but finch languages might follow completely different organizational principles, grammatical structures, and semantic systems. These differences could reveal fundamental constraints on communication systems that transcend specific biological implementations. The potential for interspecies communication would raise fascinating questions about translation protocols and conceptual frameworks. Human attempts to communicate with other intelligent species have been limited by cognitive and linguistic barriers. Language-capable finches might provide the first opportunity for true interspecies dialogue, revealing whether different evolutionary origins produce compatible or incompatible cognitive frameworks. Conservation implications would become critically important if such remarkable cognitive abilities emerged. Language-capable finch populations would represent irreplaceable evolutionary achievements, requiring unprecedented protection efforts. The loss of such populations would eliminate millions of years of unique evolutionary development and potentially humanity's only opportunity to study alternative intelligence evolution. Technological collaboration possibilities might emerge between human and finch civilizations. Different evolutionary origins would likely produce complementary technological specializations based on distinct anatomical capabilities and environmental challenges. Human societies might benefit from Finch innovations in areas like aerial navigation, environmental monitoring, or resource distribution, while Finches might benefit from human technologies for communication, construction, or energy production. Educational system integration could revolutionize our understanding of learning and knowledge transmission. Finch educational approaches, developed independently from human cultural traditions, might reveal more effective teaching methods, learning strategies, or knowledge organization systems. Comparative educational research could identify universal principles of effective instruction applicable across species boundaries. The emergence of Finch literature, art, and cultural expression would provide unique perspectives on existence, environmental relationships, and social organization. These cultural productions might reveal aspects of consciousness, creativity, and aesthetic appreciation that human-centered perspectives cannot access, expanding our understanding of the possible range of intelligent experience. Space exploration applications could benefit dramatically from Finch cognitive abilities and cultural perspectives. Their natural flight capabilities, enhanced by technological development, might provide unique advantages for exploring planetary atmospheres, conducting aerial surveys, or maintaining orbital installations. Finch spatial reasoning abilities, evolved for three-dimensional flight navigation, might surpass human capabilities for certain space-related tasks. Ethical frameworks would require substantial revision to accommodate the rights and interests of alternative intelligent species. Current ethical systems are designed around human cognitive capabilities and social needs. The emergence of Finch intelligence would necessitate developing universal ethical principles applicable across different evolutionary origins while respecting distinct cultural values and behavioral patterns. The potential for accelerated human development through interspecies collaboration could transform civilization advancement. Two independent intelligent species working together might achieve technological and cultural breakthroughs impossible for either species alone. Complementary cognitive strengths could accelerate scientific discovery, artistic innovation, and social problem-solving. Long-term evolutionary implications would extend far beyond current Finch populations. The establishment of stable language-using Finch civilizations would create new evolutionary pressures affecting all Galapagos species. Co-evolution with intelligent finches might drive enhanced cognitive abilities in other species, potentially leading to a cascade of intelligence evolution throughout the ecosystem. The ultimate question remains whether such remarkable cognitive evolution is theoretically possible within realistic timeframes and environmental constraints. While the scenario represents an extreme extrapolation from current Finch capabilities, the underlying evolutionary mechanisms, neural plasticity, cultural transmission, and environmental pressure exist throughout the natural world. The emergence of human intelligence demonstrates that remarkable cognitive evolution can occur. The question is whether it can happen twice through different pathways on the same planet. Understanding these possibilities expands our conception of intelligence, communication, and consciousness beyond human-centered assumptions, revealing the vast potential for cognitive diversity throughout the universe and the precious rarity of the intelligence that has already emerged on our remarkable planet.